Hello. So last time we talked about the one-shot deviation or the one deviation property or principle, right? So intuitively, the one deviation property essentially says that a strategy profile of a finite multi-stage extensive form game with perfect information or observed actions, it is a subgame perfect equilibrium if and only if there exists no profitable single deviation for each subgame and every player, right? So that's essentially the intuition of the one deviation property, right? So even simpler, so it says that so if no player can increase their expected payoff by deviating from their original strategy via a single action in just one stage of the game, right? Then the strategy profile in SPE, then the strategy profile is SPE, right? Or in other words, no player can profit by deviating from the strategy in one period and then revert into the strategy. Okay, so that one deviation property allows us to check for a SPE where the for each player in every subgame, the initial action would be would has no deviation to have a profitable deviation, right, from the equilibrium strategy. So that's how we check for the SPE, right? Okay, so in this new episode, we'll discuss a new theorem called Kuhn's theorem. Okay, so essentially it gives a the existence for the SPE. Okay, so essentially it says that every finite, okay, extensive game with perfect information has a subgame perfect equilibrium. Okay, so this looks true, right? But we have to prove that, right? And the approach of this proof is by the mathematical induction. Okay, and it's sort of a dynamic programming, and it's solving this game backwards. Okay, so the basic idea of that is to construct a sort of a function, okay, and which associates a terminal history and for each history and shows that this history is a subgame perfect equilibrium outcome of the subgame with that history. Okay, so we can imagine that from the end of the game, from the terminal histories, the outcomes, then we could step by step and solve backwards, and to solve in each subgame from backwards, which is the optimal action or which is the optimal strategy in that subgame for this player to choose. Then after we solve that, then the other the other strategies or other outcomes are deleted or removed from the subgame, right? And then we further move backwards, right? Move up from the game tree, and then solve the second last subgame, and so on and so forth, right? So that's essentially how we find a subgame perfect equilibrium, and that's also how we prove this theorem, right? And that's just a constructive proof. Okay, so now let's do that. The proof. So you could refer to the textbook if you have some confusions in any part of the proof, right? Okay, so let this gamma to be still the finite extensive game with perfect information. So the player's histories and the player to move at some history, right? Remember from the previous episodes, and preference relation. Okay, so this is a finite extensive game with perfect information. Okay, so we just skip that. Okay, you know. And then we construct is SPE. Okay, of this gamma by some induction. Okay, on the length. Okay, remember this is L, length of a game with some history H. Okay, so at the time we simply define a function. It's called R function. Okay, as mentioned in the textbook. So this R function, which associates a terminal history with what? With every history H. Okay, so essentially this R function, it always associates a terminal history. Okay, with every any of the history in H, and show that this history is a SPE outcome of the subgame gamma H. Okay, and it constructed SPE from the terminal from the last subgame, right, and then goes all the way up and then solve the whole game. The whole game, of course, it is a subgame of itself, right? And then it finishes. So that's the basic idea of this proof. Okay, so specifically, if the length of gamma with history H is 0, if this is a special case, right? So if it doesn't have any length, so it means that H is just a terminal history, right? Of gamma. Okay. So if so, then we should just say that RH is H, okay, for simplicity. All right, so now suppose that this RH function is defined for all H with the length of the subgame H. So this length is no greater than some number K, okay, for some non-negative number, okay. All right, so so that's the first step. All right, and then let some H star be a history, okay, and this history where the length of gamma with H star is actually K plus 1, okay. So it means that in this case, this length is one longer than a K, right? But the maximum here with this H would be just K. All right, so that's the difference. And also let P to the player with his H star is for player I to move. Okay, so those are just some definitions. Okay, so far. So now is the argument. Because the length of gamma with history H star is k plus 1, okay? That's true because we define that to be so. We have the length of gamma of a subgame with history H star and some action A, right? So this is no greater than k for all the action with history H star, okay? And further, we define SI H star. So this is how here is the most important part where we construct the subgame perfect equilibrium strategy right here. So we were constructing the strategy profile and specifically we're doing that for each player, right? So so how we do that is to define this SI for some history H star to be just the one that maximizes the utility for this player, right? To be a preference relation for player I, this relation maximizer. Okay, so this is kind of weird, but it's essentially it means that this strategy here it maximizes the player's payoff, right, in this subgame of this R given H star and A, okay, and this is over the A with H star, right? Okay, and correspondingly define R H star, okay. So what that should be, we simply let it to be R H star, and the action would be the optimal one, right, for this strategy here in equilibrium. Okay, so now this looks like a subgame perfect equilibrium, right, for this subgame. So the strategy S star, SI star, SI H star would be the strategy, right, in equilibrium. So and by induction, so since we have that for the last, for the very end or the terminal, for those subgames at the terminals, right? So we have those to be true. Then we by the induction we have all those others one by one, and then gradually get all those subgames. Get all those equilibrium strategies in all those other subgames, right? So by induction, we have already defined a strategy profile, right? Because we have each player I for all, in the for all players, right? Strategy profile S in this gamma, okay. And further, by the one-shot deviation or the one deviation property, okay. By one deviation property, because here in each subgame and for each player, it satisfies the requirements for the one deviation properties, such that the only difference would be for each player and for each subgame. The only difference is just the initial move that in each subgame, right? And for each player. So that's the only difference between the deviation, profitable deviation, and the equilibrium strategy, right? So by the one deviation property, the so the strategy profile is a subgame perfect equilibrium of gamma itself, right? Okay. So up to here, we have proved, or we have successfully constructed the subgame perfect equilibrium for each finite extensive game with perfect information. Right. So so the procedure used in this proof is referred as the backwards induction. Right. Okay. So this proof is essentially is a backward induction. Okay. And essentially this is it is demonstrating some algorithm, right? But when we're using math to express those algorithm, and it looks pretty tedious, right? Okay, so but essentially what it means is this. Okay, let's go back to the example. All right, so there are a lot of Nash, but we're not looking for Nash. We're looking for the subgame perfect equilibrium, right? Let's have some pink. Okay, maybe right here. Okay, good. So now let's solve backward. Okay, from the farthest subgames. Okay, which are the closest ones to the terminals. Okay, let's look at the first subgame here. Right. So here, since player 2 is going to move, right? So here, player 2 would choose either Y or N. So it has no difference, right? Okay, so here, those two outcomes are both possible here, right? Okay, so if, and now we go to this subgame here, right? So since this 1 is strictly greater than 0, so for this subgame, player 2 must choose this Y, right? Okay. And how about the last subgame here on the right hand side here? So since Y has 2 and N has 0, so player 2 must choose this Y, right? Okay. So in this case, we just delete or remove the other part, right? So it means that this path is directly connected to here. That's essentially what the algorithm or the proof says, right? So we just delete the other one, which is not the equilibrium strategy. Okay, and go from here and directly to here, right? Okay, but here it's possible to be either here or here, right? Still possible. Okay, so given that, then what the then we go up, right? So we finish the last stage and then go back to the first stage when player 1 was going to move, right? So what was player 1 thinking about? Okay, so given the behavior of player 2, okay, so in this case, player 1 could get either 2 here, right, or 0 or 1 or 0, right? Okay, so and if player 1 chooses this 0 2, this action here, then it means that it has to go to this place, right? So player 1 gets 0 for sure. But if player 1 chooses either 2 0 or 1 1, if those two actions, right, or those two strategies then player one could get maybe 2 or 1. Okay, not necessarily 0, but there's a 0 here, but it's not necessary, right? So then in this case, player one must delete or must not consider the third option, right? So this one is also removed from the picture, right? So the only so the possible thing is that, okay, so if, let's say, if player two, so player two, from the perspective of player two, it has the same payoff for the player two, either choosing y or n here, right? So if player two is going to choose y, okay, so if that's the case, all right, and then we remove this from the picture for now, and then the only thing that we need to compare is this y. So is this outcome and this y and this outcome, right? So it means that here player one will of course choose this 2-0 because player one could get 2. And in that case, this equilibrium outcome would be y and 2-0, so it gives 2-0 payoff. Okay. And let's go back for a second. If player 2 was going to choose this n here, okay, in this case, then player 1 must choose this 1, right? So that in this case, player 1 could go directly from here to here, right? In this case, player 1 could get 1, but here player 1 could only get 0, right? So gets nothing. So then in that case, we get the other subgame perfect equilibrium, so which is 1 and y, right? So this one, and each player gets $1. So those two payoffs for from those two outcomes are those two strategies are the equilibrium strategy profiles for this whole game, right? So those are the subgame perfect equilibrium. Okay, so although the proof or the induction part is not very straightforward to understand, but the algorithm itself is pretty simple, right? We just solve backwards from each subgame, as we just mentioned, and from that we could just get our obtain our all of those subgame perfect equilibrium, right? Those strategies that we need in equilibrium. Okay, all right. So that's the example that we used for illustrating the the idea or the intuition for this algorithm of the backward induction in finding the subgame perfect equilibrium. Okay, which is just some examples for the Kuhn's theorem. Okay.